One part of ergodic theory is concerned with the structure and classification of measure-preserving transformations. And our next definition gives the two basic relationships that may be between two measure-preserving transformations. So here's a definition. 2.7 as in the book. Let x b sub x mu t and y by nu s be two measure preserving systems. Remember, those b sub x, b sub y's are sigma algebras on those spaces, and mu and nu are probability measures, and t and s are measure preserving transformations on those spaces. So t is from x to x, and s is from y to y. And now here are two definitions. First, the system y by nu s, named the second system, is called a factor of the first system, x bx mu t, if there are sets x prime in bx and y prime in by with full measures, namely mu of x prime is 1 and mu of y prime is 1. And we further assume that x prime is invariant under t and y prime is invariant under s. And by that we mean tx prime is contained in x prime and sy prime is contained in y prime. And there's a measure preserving map phi from x prime to y prime with phi composed with t applied to x is equal to s composed with phi applied to x for any x in x prime. Okay, so at this point you might wonder what's the point of taking x prime and y prime in the definition. So if you remember that when I talked about this at the beginning, I said every map of function, so in the measure theory, is only considered defined almost everywhere. It doesn't have to be defined everywhere because its behavior on a set of measure 0 does not affect its properties. So in this situation, as long as we have subsets of full measure and we define our function over there, we are good. So x prime almost represents x and y prime almost represents y. So that's enough. And in this way, we will allow some flexibilities. Okay, now second definition. The second definition is almost the same as the first one, except that here, instead of just being measure preserving, we require that this map to be also invertible. And in that case, we'll call those two systems isomorphic. So the only thing that's going to be changed in this definition is first, instead of just measure preserving, we'll put that this is an invertible measure preserving map. And if this is satisfied, then we say the system YBY new S is isomorphic to the system XBX mu T. And I should highlight their differences. As you can see from this last sentence, if you know algebra very well, you know there's a commutative diagram involved in here. Namely, we'll have this. This diagram is commutative, except for on the sets of measure 0. So to be rigorous, I have to put primes here. So x prime and y prime. But usually it is understood that in measure theory we are only concerned with properties that hold almost everywhere. So it will be okay for us to remove those primes. So it's okay for us if we just write it in this way, with the understanding that those T and S phi are not defined everywhere, but almost everywhere. At this point, there are some remarks that I would like to make about this invertible measure preserving map. Suppose we have a measure preserving map phi between two probability spaces, say from x b mu to y c nu. So this is a measure preserving map. And remember, by measure preserving, we already assume that phi is measurable. So I should emphasize that this is measurable by definition of measure preserving maps. Some people, when they see measure preserving, they may not remember that this is measurable. But in order to check something is measure preserving, we first have to check that this map is already measurable. Phi is called invertible if there exists a map, say psi, from the opposite direction, y c nu to x b mu, that is also measurable and measure preserving. And that this psi is really inverse to phi. Namely, so if you compose them, you should get the identity map. And it should be understood that everything going on here is happening almost everywhere. They do not have to happen everywhere. So In order to prove that two systems are isomorphic, there are a lot of things to check. First, you have to construct this phi from a subset of full measure in X to a subset of full measure in Y. You have to prove that this map is indeed measurable and measure preserving. And furthermore, you have to construct an inverse to phi and prove that inverse is also measurable and measure preserving, just like what I said over here in this remark. So it is quite complicated to check the two systems are isomorphic. But among all those properties to verify, there's one property that we don't have to check. Do you see which property we don't have to check? I'll let you think about it, but I will tell the answer anyway. It turns out that we don't have to check that psi is also measure preserving. The reason is that once we have all the other properties, then this measure preserving property is evident. It follows from other properties immediately. So I should write that you don't have to check again that psi is measure preserving. And why? Because once we have that phi is measure preserving, remember by definition that means mu of phi inverse of C is equal to mu of C for every C in the sigma algebra C. But now, for any B in the sigma algebra B, B can be written as phi inverse composes phi applied to B. You know that phi is just a psi inverse. So now you can replace C in this first equation by psi inverse of B. And what you get is that mu applied to phi inverse applied to psi inverse of B is equal to mu of psi inverse of B. So this part is just C, and this is just the first equation by replacing C with psi inverse of B. And the left hand side is just mu of B. So mu of B is equal to nu of psi inverse of B. This shows that psi is also measure preserving. So as long as this psi is measurable and it is invertible to phi, it is automatically measure preserving. We don't have to verify this. And this tells you when you want to prove two systems are isomorphic, there are only three things to check: the measure preserving and the measurability of phi, and the measurability of psi. And before we move to our example, there are a couple of more concepts that we want to introduce. A vector map from the system x bx mu t to y by mu s will also be described as an extension of our first system. Of our second system, y by mu s. Remember, so y by mu s is called a factor of our first system. A factor y by mu s is called trivial if the space Y is trivial, namely Y is just one point. And this extension is trivial if this measure-preserving map is an isomorphism. So what we did here is that we introduced a notion called extension, and we introduced two trivialities. And now we start talking about a very, very important example.